Good evening, everybody.
Hello.
Good evening, Professor.
Hello.
Okay, let's get started here. Before we get started, though, before I jump into tonight's lecture, does anybody have any questions they would like to ask? Anything? I'm going to start each lecture off this way. Encourage you to ask questions if you had any on the homework or on what you read in the textbook or where we are going with this class. Any questions at all?
Professor, actually, I had one. It was at the beginning of Thursday's lecture, so we had just finished the normal strains. So when talking about the tension and compression, can we always assume that the member, the length that's smaller, can we always assume that's going to be compressed?
Yes. Yeah.
Okay.
Yeah, the only way that you can strain something to shorten it is if you compress it. And so, I'm glad you asked that question. So if you have a compressive load on a member, then the stress in that member is going to be negative. So negative indicates a compressive stress. And if you apply a compressive stress to a member, it will shorten, and that will be considered a negative strain. If you look at the math behind it, remember strain is equal to the new length minus the original length over the original length. So if the new length is shorter than the original length, you'll have a negative strain. So we are pretty consistent about that. A negative strain is a shortening of the member, which is due to compression. A negative stress is a compressive stress. So it's all in the sign. If it's positive, then it is being stretched and it is tension. If it is negative, it is being compressed and it is a compressive load.
Okay, thank you. Yeah, I wasn't here on Thursday, so I just watched the video, so I just wanted to ask that real quick.
Okay, great.
Thank you.
That was a good question. Do I have any other questions? Okay. Hearing none, I wanted to talk about the homeworks for a moment. I've graded 2 homeworks now, and I'm starting to see some patterns. I just want to mention this before we get too far down the line. I'm pretty sure I mentioned this, but in case I did not, I will mention it again. In doing your homeworks, please use 1 sheet of paper for each problem. Do not put 2 problems or 5 problems or, God forbid, 10 problems on 1 page. It makes it almost impossible to grade. So please follow that guideline. Paper is fairly cheap, especially if it's digital. Please use a whole sheet of paper, even if you're only using 3 lines for 1 problem. So 1 problem per page. I have started docking points for that, and I wanted to make sure that everybody was aware of why those points are being removed. 1 problem per page. Speaking of which, grading, I've graded homework 1 now, I've graded homework 2 now. Anytime I take away points, I put a little comment tag on your homework saying why you lost some points and what the issue was. So please review your homeworks and look for those comment tags to see what went wrong. Okay, is everybody clear about 1 problem per page?
Yep.
Very good. Okay, great. The next one is, and I haven't started docking this one yet, but if it continues to be a problem, the other one is when you read the problem, each one of these homework problems is asking for something specific. It's asking for the stress in member BC. or it's looking for the deflection at node D, whatever. Whatever it is that the problem is asking for, please box those answers. And most of you are doing a great job of boxing those answers. I thank you very much. But some of you are boxing all of your answers. So having none of the numbers boxed is just as bad as having 9 of them boxed when I'm only trying to find one. So please box your final answer, but please only box your final answer, or highlight, or whatever it is you're doing to point out what it is you want me to see. Please don't do that to all your intermediate steps. That only belongs to the final answer. And again, this is just to facilitate me being able to go through, I think we're at 34 papers now, so going through 34 papers. But the easier it is for me to find your final answer, the happier everybody will be. And then finally, I hate to mention this, but I feel that I must. Some students, and I get this every semester, but I have some students that clearly from the homework, they are just copying step by step out of a solution manual or somebody else's homework, or I don't know, I don't care. But it is clear that somebody is just copying the solution manuals without actually calculating or thinking through these problems. If there's a whole bunch of work missing, it becomes quite obvious that it was just copied from some solution. Or it's left for me to assume that it was just copied from some source. What I want to say about that is, although you are copying all the proper steps and you're getting all the proper answers, and you may be scoring 17, 18, 20 points on the homework, I can tell you from experience that you are really shooting yourself in the foot with a shotgun so that you can't possibly miss. What you are cheating yourself out of is the struggle. And without the struggle, you don't gain the skills. Without the skills, and I do mean skills, not knowledge, but without the practiced skills, I have seen this time and time again, that the students who do not struggle with the homeworks struggle on the midterms or the final exam for that matter, and they do not do well. There's always a very direct correlation to those who take the easy way out on the homework and those who really, really score poorly on the tests. So this is public announcement, public service announcement. I don't know how else to say it, and I don't know. I'm only speaking to a few, maybe, but if that's the way you want to do the course, then I can't. You know, it's hard if you put down all the steps and you copy down all the work, then you will get good grades on your homework, and really, really good grades on your homework, and scoring a 12 out of 50 on your midterms is not going to cut it. So I don't know. Do I need to say any more about that, or is that pretty clear?
That's clear.
And I'm not pointing anybody out. I don't even know. I don't know. You know, sometimes I can't tell. But even if you are using the solution manual as basically just copying, and you're really good at it, and you copy down every single step, and I can't tell the difference, you're still cheating yourself, and it will come out in the tests. I've graded hundreds of tests by now, and I can tell. who has struggled and who has not. Now, that is not to say that I know a lot of you are using the answers in the back of the book and or solution manuals to check your work. And I have no problem with checking your work. But if you cheat yourself out of the struggle, you cheat yourself out of practicing and perfecting your skills, then you're cheating yourself. Okay. Now that that is behind us, let us start our lecture number 6. Any questions before I start? Okie doke. Okay, so tonight we are starting strain energy. Let me find real quick where we are. We are, let's see, there's that guy. We talked about that. Okay, so for your reading, we are in section 3.4 of the textbook. I highly recommend that you roughly follow the lectures by your reading in the textbook. I have found many students have had good success in reading those sections first and then listening to me talk about it, and then you have questions because you've read it and there was things that didn't make any sense. You could ask questions during the lecture. So I highly recommend that you read ahead a little bit, but at least follow behind and keep up on your reading. So we are in section 3.4 tonight, and the topic is strain energy. Okay, so energy. What is energy? Energy is equal to work. Everybody remember energy and work from your physics courses?
Yeah.
Okay, good. And so everybody remembers that basically work is a force times a distance. That's the physical definition of work, is a force applied through a distance. Or a force times a displacement, same idea. The units of which are pound-feet or kip-inch, or energy in the SI is joules or Newton meters. Anybody know what the unit of energy in the US customary system is, other than foot-pounds or kip-inches? Anybody? No, very close, but a watt is actually a measure of power in the metric system. The unit of work in the US customary, there's actually a few. Joules is SI, that's joules here. Anybody heard of such a little thing called a calorie or a kilocalorie?
Yes, we took it.
Calories is a measure of energy. A calorie is a measure of energy, which makes it also a measure of work. So when you eat that Chipotle burrito that has 2,300 calories in it, those are actually 2,300 kilocalories, and you have put that much energy into your body. And so you must understand that this is energy, and either use that energy or you're gonna save it for later. So that's the beauty of a calorie. What else do we have in the US customary? Something that most people have never heard of in their lives. It's called a BTU. Anybody heard of a BTU?
They use it in
Yes.
growth.
British thermal unit.
British thermal unit, yes. And it's usually used in like HVAC applications, heating and cooling. like when we bought my son a portable air conditioning a few years ago. And if anybody can actually see me and wonder why I'm always dressed like I'm in Alaska, he likes it a little cooler. I like it a little warmer. So we got him a portable air conditioner. You can read right on the box from Lowe's how many BTUs this unit will cool. And I forget what it was, 2,700 BTUs, 200, I don't know. But it seemed kind of ridiculous that nobody knows what a BTU is and they're advertising this. But anyway, that's more of a standard unit in the US customary for energy in terms of heating and cooling. You'll see furnaces rated in BTUs. Okay, but that's doesn't really help us much here. We are not going to be using calories. We are not going to be using British thermal units. 8,000 BTU, there you go. Thank you, Justin. And exactly, like it says 8,000 on the box. Oh, well, shoot, that must be a good one then. Okay. Before we go there though, one other thing I want to say about energy and work, just to kind of paint a picture. If in our family we do a lot of hiking, not when it's 121 degrees in Chino on Sunday, but other days we like to do hiking, and so we will hike up our local mountains. We'll go to Mount Baldy or Mount Wilson or whatever. If I were to hike up a mountain and it takes me 10 hours, how much work have I exerted? What is the level of work that I have done? How would you calculate that? Well, work is a force times a distance. When I walk up a hill, what is the force that I'm exerting? Well, I'm resisting gravity. So basically the force is mass times gravity. Yes, the force is my weight. Now, I'm going to tell you what my weight is, but I'll tell you that the work that I exert hauling my butt up the mountain is my weight times that distance. Well, what distance are we talking about? It's the distance that is in the direction of the force. So even if I was to hike 7 miles, 7 miles is more or less a horizontal distance, not the vertical distance. So it's only the vertical distance that matters because that is the direction of the force being exerted by my body. So the work that I exert is basically my weight times the elevation gain from where I started to the top of wherever I quit. That's the work, right? So if you were to say 200 pounds times 1,000 feet, well, then that's 200,000 pound-feet of energy or work. So does it matter if I hike up starting at the trailhead and I hike to the top of the mountain and it takes me 3 hours to get to the top of the mountain? And then my son, he's on the track team, of course. So if my son runs up that same trail and he gets there in 45 minutes, who has exerted more work? Anybody?
Should be same.
It would be the same.
Depending who's heavier.
Depending on who's heavier. Exactly right. So I've done more work, thank you very much. He's, again, on the track team. I am not. So strictly speaking, work-wise, I have exerted more energy than he has because we went the same vertical elevation change and I weigh more than my son does. But you're saying, well, wait a minute. You walked, he ran. Didn't that count for something? And it took me 3 hours. It only took him 45 minutes. Doesn't that count for something? I'm painting this mental picture because a lot of folks get confused about the difference between work and power. Power is the exertion of work or energy over time. Work or energy is just the total force times a distance, whereas power is force times distance over time. That's the difference. You betcha he's putting out 3 or 4 times as much power as I did getting up the same mountain. He can exert a lot more power than I can, but that's power. Okay, so power is kip inch per second or joules per second or Newton meters per second, or as somebody said in the chat, watts. Power is watts, or in the US customary, horsepower is what we use a lot, is horsepower. Horsepower is, let's see, 700 something watts is 1 horsepower, something like that. But it's horsepower in the US, it is watts in the SI. Do not confuse power with energy, okay? So we're not gonna talk about, I would love to talk about power and engines and motorcycles and whatever, but that's not this course. Okay, so is everybody clear on energy, what we're talking about with energy? Okay, so moving on. If we consider a cube of material, so here's some material of a size delta y by delta x by delta z, and we apply a force in the z direction, like so. So remember, force is a stress times area, and the stress is just going to be sigma, but the area is delta x times delta y. So my delta F force is stress times area. If I apply this force, then I'm going to get some deformation. And that deformation is equal to the average normal strain times the height, delta Z. Okay? And this is kind of what we've already been talking about. We've been talking about stress and strain. So a delta force produces a delta, a deformation as such. So strain is the new length minus the original length over the original length, which is equal to delta over the original length. So delta is equal to strain times the original length. So the deformation is strain times length. So delta is equal to strain times delta Z, because the original length of this cube is delta Z. And the force is stress times area. So delta F is the force, sigma times delta X, delta Y. So work, we use the symbol W for work, is the average force times a distance. So here's a chart. The vertical axis is the applied force. The horizontal axis is the deformation, as shown here. If I apply a little bit of force, I get a little bit of deformation. I apply more force, I get more deformation. And this, of course, is a straight line because we are talking about a elastic, linearly elastic material. So if I double the force, I get double the deflection. So far, so good? Okay, so the work exerted is the average force it took to get to delta, the average force. Well, the average force, say the force was 0 at the beginning, the force is delta F at the end, so the average force is delta F over 2, as you can see here. So work is equal to delta F over 2 times delta is the distance. And this has a physical significance that it is equal to the force under, area under the force displacement diagram, like so. So if I was to plot a force displacement diagram, then work is equal to the area under that curve. Okay, everybody still with me?
Yes.
Thank you, good. So the work is equal to delta F over 2 times delta, but delta F is equal to sigma times delta X delta Y, and delta is equal to epsilon times delta Z. So stress times area, strain times length. I just made these substitutions here and here, substituted in here, which gives me 1/2 sigma epsilon delta X delta Y delta Z. Which I just repeated here. So we have this thing called strain energy density. If I have my volume, the volume of that cube, delta V, is delta X times delta Y times delta Z. So if I take an internal energy, strain energy, is equal to the external work. So U is the internal energy, W is external work. And think of energy stored in a compressed spring. So if you have a spring and you apply force to it, that spring is going to compress or elongate. And once it is compressed, you have energy in that spring, as you know. And if you were to release that spring, it would release that energy again. So that's this concept here, that external work applied to the spring produces internal energy, but it's called a strain energy because you strained the material and kind of compressed it like a spring. So internal energy, strain energy, U, is equal to your delta U, which is the work, divided by the volume. So if I take my work, 1/2 sigma epsilon delta X delta Y delta Z, divide by the volume, then I have a simplified version of 1/2 sigma epsilon. This is my strain energy density. And it's called strain energy density because this is really energy per unit volume. And it's a lot easier to work with this way as a per unit volume. Okay, so as we learned before, that strain is equal to sigma over Young's modulus. This is Hooke's law. Then we have substituting U, 1/2 sigma epsilon is equal to 1/2 sigma times sigma over Young's modulus, or 1/2 sigma squared over Young's modulus. So either of these are valid for internal energy or strain energy density U. Either of these two are equivalent. Any questions? Okay. The units of strain density are kip inch per inch cubed. And yes, I do realize that this is the same thing as KSI. So I can take inches over inches cubed, and that washes out. So that'd be kips over inch squared. Kips over inch squared is KSI. But KSI more aptly describes a stress, whereas work is kip inches per volume. This actually describes what we're talking about better. We can also use Newton meters over meters cubed, or we can use joules per meter cubed. Same idea, this is energy per volume. Okay, any questions on that concept of energy? Okay. So we're going to talk about this thing called modulus of see if I can say it, resilience. The modulus of resilience is the energy required to bring a material to the proportional limit. It is abbreviated with a mu. So the little fancy U is a mu sub R, and it is equal to the area under the stress strain diagram from the origin to the proportional limit, like so. Remember, this is a stress strain diagram for a ductile material. You have your elastic range, the proportional limit, yielding, strain hardening, and fracture from last time. So the modulus of resilience is just a measure of how much energy can a material take before you have pushed it out of the elastic range. And it is equal to the area under the elastic portion of the stress strain diagram. So because this is a straight line, and that makes this a triangle, and we know the height of the triangle is the stress at the proportional limit, and the base of the triangle is the strain at the proportional limit, then we can come up with an equation that describes this area. So the modulus of resilience is equal to 1/2 sigma, and this is PL is proportional limit squared over E. The modulus of resilience represents the maximum energy per unit volume that a material can absorb without permanent strain or damage. So that's an important concept. You can have a spring and you can figure out how much energy you can put into that spring. You could derive the energy from a force, of course, but it's really a measure of energy. And if you have that spring and you put too much energy into the spring, you're going to permanently stretch that spring out. And it would have a permanent strain in it, or you'd consider it to be damaged if it was like the spring supporting your car or something like that. So that's the modulus of resilience. Next, we have this thing called a modulus of toughness. And it's a similar concept, but the modulus of toughness is the energy required to bring a material to fracture. How much energy does it take to actually break the material? Mu sub T is the area under the stress strain diagram from the origin to the point of fracture. So it's the area under the whole curve from 0 all the way to fracture. Modulus of toughness represents the maximum energy per unit volume that a material can absorb before fracturing. This is a measure of toughness, not necessarily strength. This property can be very important in seismic design as just one of many, many examples of where toughness might come in. Guys, pardon me for just a second. I will be right back. Okay, I'm back. Okay, can everybody see this image? Anybody know what this might be an image of?
From what I can see, it looks like something collapsing, like a tunnel.
Okay, yeah, I can see that. I guess that's a bad image. It is a fracture in material. Yes, yes, that is what it is. Okay, it's a little unfair to ask that when you don't have any context. But what you are looking at is a connection between a steel beam and a steel column. And that right there, which kind of looks like a tunnel, I see it now, is one big monstrous crack. So this beam has a big old honking crack right through it. And honking is a technical term you don't need to concern yourself with at this point in the game. Here's a side view elevation, kind of a diagram of what it is you're looking at. So this was a beam web. This was the panel zone. This is a very heavy flange of a column. And these are the types of cracks that they saw in the Northridge earthquake. So that's what we're talking about. We're talking about beam column connections that had cracks in them like this. And it was very prevalent after Northridge. So pre-Northridge, steel moment frames were designed strictly on the basis of being strong enough. Many frames cracked and failed not due to a lack of strength, but rather a lack of toughness. So when you design moment frames, particularly before 1994, when you design moment frames, we basically would just use equations to derive what the loading demand is on the building. And then we would design this beam and this column and this welded connection and everything to resist that level of strength or loading without a whole lot of consideration of toughness. Since Northridge, the welded portions of the frame have to show a minimum degree of toughness by passing a test called a Charpy V-notch test. Here is the test apparatus. You have this pendulum with a hammer in it, and you take a sample and you cut a notch in the sample in a very specific way. I don't know if you can see that so clearly, but these are all dimensions of exactly how the sample has to look like. And then this hammer comes down and whacks it on the back there and breaks it. But in some way, shape, or form, this apparatus will measure the energy it took to fracture the material. And they can do this with samples of steel. They can even do this with welded samples. This could all be filler metal in a welded condition. And they will test the toughness of the actual weld material used to join beams and columns in seismic moment frames. So the Charpy impact test, also known as a Charpy V-notch test, is a standardized high strain rate test which determines the amount of energy absorbed by a material during fracture. Absorbed energy is a measure of the material's notch toughness. And I take no credit for this. This came from Wikipedia. I copied it word for word and stole the images from Wikipedia as well. So I take no credit for that. I just found it. But it illustrates the concept very well. The other big change since Northridge is the design of steel beams and moment frames were also revised from the Northridge experience. Special reduced areas, as shown right here, or dog bones, were introduced to promote and control yielding. So again, we kind of walked away from all strength-based. Everything needs to be stronger than the minimum load that we need. And who cares how strong it is, as long as it is stronger, everything's fine. And that's just, it didn't work very well. There were many, many failures of steel beam column connections in office buildings and all kinds of buildings all through LA after Northridge. So what we're doing now is we're reducing the size of the flange and we're pulling that reduced size away from these welded connections so that this portion in the top and bottom flange most certainly is going to yield during a seismic event. It shouldn't fracture, but it will yield. and it's going to absorb and dissipate a lot of energy in this area here while pulling that energy away from what is more brittle. The brittle is the welded portions of this. So the welded portions of this need to remain strong. They should not be yielding and stretching and getting ready to fracture. So this is another way that we've incorporated toughness into our frames by getting the yielding mechanism away from the somewhat brittle end region of the beam. Since the modulus of toughness is found by the total area under the stress strain curve, the strongest material is often not the toughest material due to the high strength material's lack of ductility. So again, I just pulled this off the web. I thought it was a nice illustration. You could have a material that is very high strength, but once it fractures at a fairly low strain. So the area under this curve here is fairly small, even though it's very high strength. You could have a material that's fairly low strength, but and it has great ductility. It goes way out to this strain here, but still the area under this curve is somewhat inferior to this material in the middle that is, I don't want to say medium strength, it's still a high strength, but it has good ductility as well. So it has a high total stress and it has a high total strain, which combining these two together gives you the greatest area under this curve. This middle material here is going to have the best toughness characteristics.
What would be an example of a material like that?
Okay, great question, great question. Okay, this material here, this high strength, low ductility material would be an example of like high strength bolts. They're called A490 bolts. They are very, very strong, but they lack ductility. Even more so, in my world, we use something called a pre-stressing strand. And the wires in the pre-stressing strand, each individual wire is very high strength. Just to put some context in this, regular structural steel that you see in bridges and buildings nowadays is about 50 KSI. That's the stress at which it starts to yield. This strand material has a fracture point of 270 KSI. On this chart here, here's 60, here's 270, but the material is very brittle. The strand material is brittle. So it would follow a curve just like this, and then it snaps, it just fractures. So strand, each individual wire in the strand has low toughness. It would not do very well at all. And so you're probably thinking, well, why are you using it in concrete? Well, it's only because we're taking these very, very high strength wires that are brittle and we're weaving them into a strand of 7 wires per strand. And then it acts more like a rope and that you get your ductility back. But that type of steel is an example of a high strength, low toughness material. Another good example is tool steel. The steels that you use in tools, like if you ever go to a machine shop and you watch them turn a lathe and well, you know, like a like a machine shop where you would take like a crankshaft to a machine shop and they would turn the bearings. Well, the tools that they use to shave very precisely shave the metal off of a bearing journal is a steel. It's a tool steel. It's very, very strong, but it's brittle. So if you overloaded it, it would just fracture. It's almost like a diamond more than like steel. The middle ground, this middle stuff here, are your structural steels, like grade 50, A572 grade 50 for buildings, and like A706 grade 60 KSI rebar for concrete. That would be an example of high strength, but very good ductility. So you have a good toughness in these steels here. Low strength, high ductility steel would be more like A36 steel, which is just what we called mild steel. And that stuff's not very strong, but it will bend for days. Almost, almost like the steel you find in a paperclip. That's very ductile, but fairly low strength steel. Did that answer your question?
Yes, it did. Thank you.
Awesome. Okay, let's do some examples, put some numbers to this. If we want to find the modulus of resilience for the following material from a given stress strain diagram. Okay, so here's my stress strain diagram, and I want the modulus of resilience. Solution. From the stress strain diagram, and you're gonna have to trust me on this because it's too small for you to eyeball, but if I measured where that proportional limit occurs, where the straight line ends and the curve starts, that happened at a stress of 43 KSI, and it happened at a strain of 0.002 inches per inch. And I was able to measure that because I did this on CAD. So the modulus of resilience, mu sub r, is equal to half times the stress of the proportional limit times the strain of the proportional limit. So I have half times 43 KSI times 0.002, and I get 0.043 kip inch per inch cubed. And that is our answer for this material. Okay, any other questions on energy?
No, but sorry, can you go back just for a minute?
Sure, yep. You want to point out to everybody how you box your final answer?
Yes, that's exactly.
Okay, this is a whole different topic. Okay, so that was our energy component. And we're going to come back to energy at a future time when we're going to use energy as a tool to get to other results that we want to find later on in the course. So please don't confuse or don't get confused that Poisson's ratio has nothing to do with energy. We're moving on to a new topic. And the topic is Poisson's ratio. Poisson discovered the relationship between longitudinal strain. It capitalized these. I'm so upset. This is supposed to be epsilon sub long, and transverse strain, which is epsilon sub lat. And that really bothered me. Okay, that's slide 88. And we will fix that. Okay. So, yeah, okay. So epsilon, we've been talking about epsilon now for a couple of lectures. And epsilon represents strain. And epsilon, as we just saw, is equal to L minus L naught over L naught. Well, that epsilon and epsilon long are the same thing. Epsilon long and epsilon are the same thing. It's just that I now have to distinguish between longitudinal strain and transverse strain for this particular topic, okay? So that's not to say that from now on, I will always call it epsilon long. I'm only calling it long or lat when I need to differentiate between the two and it's not obvious from the problem. Okay, is that clear for everybody? Epsilon that we've been talking about and epsilon long are one and the same. Okay, so if we start with a cylinder of length L and radius R, like so. So here's my cylinder, it is L long, and the radius is R. If I apply a tensile load P, like so, then I will get a deformation. We will see a deformation of delta. And this came out kind of small, but this is delta over 2 and delta over 2. So half of the stretching is at one end, half of the stretching is at the other end. Well, then delta is equal to epsilon long, which is what I wanted that to look like, times L. And we learned this before. So the deformation, the total deformation of this rod is the longitudinal strain times the original length, L. Where epsilon long is the same average normal strain as previously defined as epsilon. What Poisson observed was that when the bar elongates, the radius is reduced, like so. If you can see the difference right here. So if you stretch out some material and the material gets longer, then the diameter of the material gets smaller. It's an inverse proportion. If I were to compress the cylinder would get shorter, the diameter would get bigger. So what I call this is the difference on the radius. Delta prime is the change in the radius, and delta prime is equal to the lateral or transverse strain times the original radius. So I have delta in the long direction, I have delta prime in the cross-sectional direction, I have strain in the longitudinal direction, I have strain in the lateral direction, like so. So delta prime is the change in the radius. And all of this is only valid within the elastic range. Poisson's ratio is symbolized with the Greek letter nu. It's kind of like a squiggly V, but this is known as nu. And nu is defined as the negative of the lateral strain over the longitudinal strain. Nu is material specific. It is defined for each material. Nu is greater than 0 and less than half for all materials. For steel, nu is about 0.32, and for concrete, nu varies from 0.15 to maybe 0.17. The values of nu for different materials are also listed on your back cover of your textbook for all the different materials that are listed there. Okay, do I have any questions about Poisson's ratio?
Professor,
Yes,
is it the same thing in which the bar is compressed to where the radius would increase?
absolutely. Yes, yes, good question. And that's where this negative is going to come in. That's the negative because it's an inverse proportion. If epsilon long, if the longitudinal strain is positive, that means it's being stretched. If it's being stretched, then the transverse strain is negative because the diameter is getting smaller. That's why this is negative. If it's the opposite, if you're compressing the cylinder is getting shorter, so epsilon long is negative, and so a negative over a negative is a positive, then the lateral strain will be positive and the diameter will be getting bigger. which is just confirming what you just asked.
Excuse me, Professor.
Yes,
So what is the epsilon LIT?
lateral strain. That epsilon lat is this guy right here. It's not supposed to be elate. That was, I apologize. That's not supposed to say elate. That is epsilon lat. So epsilon lat is your transverse strain. Epsilon long is your longitudinal strain.
Okay, thanks.
Okay, and now hopefully it's clear. Let me use that symbol right there. The longitudinal strain is strain in this direction. The transverse strain is strain in this direction. Does that help?
Yes, thank you.
Okay, great. Okay, let's stop for a moment. Simeon Poisson was a fellow from 1781 to 1840. That was a little bit before I was born. And there he is, Signor Poisson. And Poisson was a French mathematician, engineer, and physicist, known for Poisson. Now, this is what's funny. You look up this fellow, and everything that he invented or discovered or wrote down, he put Poisson in front of. I don't know how I feel about that. That seems a little narcissistic, but what do I know? I've never met the guy. But that's why I wrote it this way, Poisson's process, because you look up what he did, and he is known for Poisson's process, Poisson's equation, Poisson's kernel, Poisson's, you get the idea. But this is all the things that he came up with: process, equation, kernel, distribution, bracket, algebra, regression, summation, formula, spot. There's Poisson's ratio, the only thing we care about in engineering. And I'd probably do the same, not gonna lie. That's a good one. I like that, Mario. Mario's process, Mario's equation, Mario's kernel, someday. But of all these things, most of them were in the fields of math and physics. Really in engineering, the one that we care about is Poisson's ratio. But he's the fellow, he was the man. Okay, example number 2. We are going to look at a concrete cylinder that is 12 inches high and has a 6-inch diameter. And again, I'm not going to lie, I'm coming up with a lot of concrete examples for you because that's the world I live in. These cylinders with these exact proportions are how we test the strength of concrete day in and day out. And so it's an everyday occurrence that I'll see a concrete cylinder in these exact dimensions loaded up into a compression machine, and it squeezes down on this until the cylinder fails. So I thought it'd be interesting to say, all right, well, just before this thing fails, how much does it actually shorten and how much does it actually widen due to Poisson's ratio? So that's what we're doing. These are generally about 6,000 PSI concrete. So the modulus is 4463.2 KSI, a rough number for this material. And for concrete new, Poisson's ratio is 0.15. So if we load this cylinder in compression with 57,400 pounds, say, what is the average normal and transverse strain of the cylinder, and what will be the final dimensions of the cylinder while under load? So here's my cylinder. My machine is loading it up with 57.4 kips. My solution. Okay, so first of all, stress is equal to P over A. So I got 57.4 kips over pi r squared gives me, and this is negative. I know there's no negative here, but you have to recognize that this is negative because this is compression. So my negative stress minus 2.030 KSI. Negative due to compression. By the way, in concrete design, if this concrete doesn't explode until about 6 KSI, then at 2 KSI, we're still more or less in the elastic range for the concrete. So these equations are only applicable because we're still in the elastic range of this material. Okay, so the strain, longitudinal strain, is stress over Young's modulus. So I have minus 203 KSI over 4463.2 KSI, and I have a strain of minus 4.5483 e to the minus fourth inch per inch, which is not a whole lot. Therefore, my deformation in the longitudinal direction is strain times length. My original length is 12 inches. And so my deformation is minus 0.0546 inches. Okay. I don't know if you guys can see me on the screen, but that is about, yeah, no way. That's about a human hair, maybe. It's not a lot. Very difficult to measure that much. But that is at 57 kips, how far this cylinder shrinks. Okay, so how much does the radius expand if the cylinder shrinks this much? Well, my lateral strain is equal to minus nu times my longitudinal strain. So minus 0.15 times minus 4.5483 e to the minus fourth yields 6.8225 e to the minus fifth inch per inch. But recognize, if my longitudinal strain is negative, my lateral strain is positive. It's always the opposite. So my lateral deformation is my lateral strain times the radius is 0.00205 inches. So the final dimensions of my cylinder under this 57,000 pound load is L minus 0.00546 is 11.995 inches. And my radius is 3 plus 0.00205, which gives me 3.0002 rounding up dimensions. So if I were to able to measure this very accurately while the machine is squishing it down, then this is what I would measure. And of course, box your final answers. Any questions on Poisson's ratio? Okay. All right. Final topic for today is a shear stress strain diagram. So if I have an element of some material and it is squished, so to speak, into this new dotted shape, then I have experienced a shear strain here and here of gamma xy over 2. So if the total shear strain is gamma xy, half of it is here and half of it is over here. So if I do that, if I take this material and I start squishing it like so through a shear strain, and I measure that, then you would have, for a typical ductile material, this would be the shape of your shear strain diagram. There is no clearly defined yield plateau for shear strain. Even in a material that in longitudinal stress strain had a very well-defined yield plateau, that same material in shear does not. So this would be a typical chart. We have a point of proportional limit. So this is where it goes from a straight line to a non-straight line. And we have a shear strain and shear stress at an ultimate, and we have a shear strain at rupture over here. So these are the highlights, the points on the graph. You notice that the slope of the elastic portion of the shear strain diagram has a slope to it, but instead of E, Young's modulus, we now have this G. Okay, what is G? Well, in this, the vertical axis is tau, is shear stress. Shear stress is G times shear strain, gamma, where gamma is known as a shear modulus of elasticity, or otherwise known as a modulus of rigidity. And the shear modulus of rigidity is known or is equal to, and I won't come up with this derivation, but is equal to Young's modulus of elasticity in the longitudinal direction divided by 2 times 1 plus nu, where nu is Poisson's ratio. That's where it comes in to engineering properties. So the shear strain is related to the longitudinal strain by Poisson's ratio. Okay, example 3. If a sample of steel has the following properties: Young's modulus is 29,000, nu is 0.32. What we want is find the modulus of rigidity. Solution, G is equal to E over 2 plus 1 plus nu. So I just plug and play, and I get 10,985 KSI. Box my answer. The back of the textbook rounds this to 11,000 KSI. Okay. Did I say shear strain was the last topic of the day?
Yes.
Yes.
No, I didn't. Did I?
Yeah,
Yeah,
you
you said the last topic.
Sorry, I lied. Got 2 more, but these are quick. These are, we'll probably finish a little early. And these are not so much calculations, but just concepts that you should be aware of. First concept is creep. And creep is defined as an increase in strain under constant stress. That's the definition. Creep equals increase in strain under constant stress. It does affect materials such as concrete and wood. Those aren't the only ones, but those are the well-known ones. Steel does not experience creep. Creep will cause an immediate deflection to increase by several fold over a number of years. So you could have like wood, and you put weight on a wood beam and it deflects an inch. If you leave that weight there and you come back after a period of time, that inch will now be 2 inches or maybe 3 inches. That's due to creep. Here is a chart of typical values for concrete. And what we're showing here is all 3 of these have an immediate deflection of equal to 1. This is just relative speaking. I'm not giving absolute strain. This is just a relative strain of 1 immediately. What these numbers represent is I put the load on the beam, a concrete beam, at 3 days old. I put the load on the beam at 7 days old. I put the load on the beam at 21 days old. And what this is showing is as time progresses, the strain in that concrete keeps growing. It immediately went to 1, but when I loaded it at only 3 days old, it immediately starts gaining more strain. It doubles in a few days, triples in a couple of weeks, and it keeps going until it basically levels off to a plateau. So again, this is all just very vague and generic, but what this is showing is that if you load concrete when it's very young, then it will experience a tremendous amount of creep. So again, the analogy is if I have a beam that deflects, say, 1 inch, and I come back over a period of time, I may have over 3.5 inches after a period of time. If, however, I wait before I load it until 21 days old, the total deformation due to creep is going to be much less than when I loaded it at a very early age. Okay, does that make sense? Okay, we're almost done. Fatigue. Probably what you're experiencing right about now. But we're talking about fatigue in metals. Fatigue is the effect of many cycles of loading increase and decrease on structural metals. So this doesn't really affect concrete or wood. Depending on the number of cycles, the material may fracture at stresses lower than the monostatic stress strain diagram. So think of it this way. Take a paper clip and try to pull that paper clip apart with your bare fingers. You can't do it. That paper clip's too strong. But take a paper clip and bend it, unbend it, bend it, unbend it. How many times can you do that before it just fractures? Like 3, 4, maybe 5 times. Well, that's a fatigue failure. You're repeatedly loading it and it can't take it anymore and it fractures. So fatigue can cause failure at a loading equal to or less than the design service load. Fatigue must be taken into consideration for structures such as bridges or aircraft that may support millions of loading cycles. And here's a diagram. So I could have a typical steel here, and if I only ever loaded up maybe 10,000 cycles, this steel can sustain 70 KSI. It's pretty strong steel. But if I load it up into the millions or tens or hundreds of millions of cycles, then if I load it more than, say, about 45 KSI, it will fail. So how much load you can have on the material depends drastically on how many cycles it's ever going to experience in its lifetime. And so think bridges. How many times do trucks roll on and off of a bridge? Every single day over the 50 years that that bridge is around. Or probably much more frightening. You ever get on the Southwest 727 airplane? Watch that wing while you take off. And some of those airplanes are 30, 40 years old. How many times do you think that wing is vibrating up and down every single day for 40 years? They had better take into account the number of cycles in the design of, here it is, the aluminum that is in that wing. So if they designed it up to 40 KSI, that plane's not going to last very long. But if they designed it into the hundreds of millions or billions of cycles, then they better keep that stress down here. No. You ever seen the wing fly off an airplane? No, never happens because they design here, not over here. No. Somebody at Boeing knows about fatigue. I guarantee it. So don't worry about it. I was just making an example. Material design will assure that the service stress does not exceed the endurance limit for the anticipated number of cycles. See? The people who designed that airplane kept their stresses way down here so that they would not have a fatigue problem down the line. Okay? Look at that, 6:44. You have a whole minute to yourselves. Any questions? Difference between G and E. One is a modulus of elasticity when you pull a material in the longitudinal direction, And the other G is the modulus of rigidity, which is a measure of the slope of elasticity, but in the shear direction. One's in the normal stress, one's a shear stress. For creep in concrete, why is that? Why they always cure it first? Yes, one of the reasons, yes. But the point of the concrete example is the longer you can let it cure in days before you put load on it, the less problem you'll have with creep. So if they want to build a building really fast and pour a new floor every week, you got to be careful about the creep problem. If they slow it down a little bit and only start pulling the formworks out and loading it after really letting it cure for a month or so, it'll really cut down on that problem. Any other questions? Okay, that is it for today. Thank you, everybody. And we will see you on Thursday.
Thank you, Professor.
Thank
Well,
you.
thank you.
Thank you.
Thanks, Professor.